Have you ever gazed at the night sky, stars scattered like diamonds on black velvet, and felt a sense of wonder? The vast expanse above us, dotted with countless stars, has always been a source of fascination and curiosity. Each star, a distant sun, holds secrets that have intrigued humanity for millennia. As you stand there, looking up, you can't help but ponder the mysteries of the universe. What lies beyond those twinkling lights? What is the true nature of the cosmos? These questions have driven explorers, philosophers, and scientists to seek answers, to understand the very fabric of reality, and wondered about the universe's deepest secrets. The night sky, with its infinite beauty, invites us to explore, to question, and to dream. It is a reminder of how small we are in the grand scheme of things, yet how significant our quest for knowledge can be. The stars, like ancient storytellers, whisper tales of creation, existence, and the fundamental laws that govern everything. They beckon us to delve deeper, to uncover the truths hidden in the vastness of space. What is the fundamental nature of reality? This question has puzzled thinkers for centuries. From the ancient Greeks, who pondered the nature of matter, to modern scientists who probe the depths of the quantum realm, the quest to understand reality has been a driving force in human history. Reality, as we perceive it, is just the tip of the iceberg. Beneath the surface lies a world that is stranger and more complex than we could ever imagine. A world where the rules of classical physics no longer apply, and where the behavior of particles defies our everyday experiences. How do the universe's building blocks interact to create the world we perceive? At the heart of this question lies the study of particles, the fundamental constituents of matter. These tiny entities, smaller than atoms, are the building blocks of everything we see around us. They interact in ways that are both fascinating and perplexing, their behaviors governed by the principles of quantum mechanics, a field of study that has revolutionized our understanding of the universe. Through the lens of quantum mechanics, we can glimpse the intricate dance of particles, the forces that bind them, and the energy that drives their interactions. These questions, pondered by philosophers and scientists for centuries, lead us to a fascinating field: quantum mechanics. Quantum mechanics is not just a branch of physics, it is a window into the very essence of reality. It challenges our perceptions, defies our intuitions, and opens up a world of possibilities. From the early days of philosophical inquiry to the groundbreaking discoveries of the 20th century, the journey to understand quantum mechanics has been a testament to human curiosity and ingenuity. It is a field that continues to evolve, with new discoveries and insights emerging every day. Imagine a world where the familiar laws of physics dissolve and the boundaries of reality blur. In this world, particles do not follow the predictable paths we are accustomed to. Instead, they exist in a state of uncertainty, governed by probabilities rather than certainties. This is the world of quantum mechanics, where the classical laws of physics give way to a new set of rules. It is a world that is both surreal and captivating, where the impossible becomes possible and the unimaginable becomes reality. And particles exist in a haze of probability. In the quantum realm, particles do not have definite positions or velocities. Instead, they exist in a state of superposition, where they can be in multiple states at once. This haze of probability is a fundamental aspect of quantum mechanics, and it challenges our classical understanding of reality. It is a concept that is difficult to grasp, yet it is essential to understanding the behavior of particles at the quantum level. The haze of probability is a reminder that the universe is not as deterministic as we once thought, and that uncertainty is an inherent part of reality. A world where light acts as both a wave and a particle, defying our classical understanding of physics. This dual nature of light is one of the most intriguing aspects of quantum mechanics. It is a phenomenon that has been observed in countless experiments, yet it continues to baffle scientists and challenge our intuitions. The wave-particle duality of light is a testament to the complexity and beauty of the quantum world. It is a reminder that reality is not always what it seems, and that the universe is full of surprises, where objects can be in two places at once. Thanks to the phenomenon of superposition. In the quantum world, particles can exist in multiple states simultaneously. This means that an object can be in two places at once or have multiple properties at the same time. Superposition is a fundamental concept in quantum mechanics, and it has profound implications for our understanding of reality. It challenges our classical notions of space and time and opens up a world of possibilities that are both fascinating and perplexing, and where entangled particles influence each other instantaneously across vast distances. This phenomenon, known as quantum entanglement, is one of the most mysterious and intriguing aspects of quantum mechanics. When particles become entangled, their properties become linked, and a change in one particle can instantaneously affect the other, regardless of the distance between them. This defies our classical understanding of causality and challenges the very foundations of physics. Quantum entanglement is a reminder that the universe is interconnected in ways that we are only beginning to understand. This is the captivating realm of quantum mechanics, a world that is both mysterious and beautiful. It is a field of study that has the power to transform our understanding of reality and open up new possibilities for exploration and discovery. Quantum mechanics is not just a theoretical construct. It has practical applications that have revolutionized technology and changed the way we live. From quantum computing to quantum cryptography, the principles of quantum mechanics are shaping the future in ways that we are only beginning to comprehend. A world that challenges our intuitions and reshapes our understanding of the cosmos. Quantum mechanics forces us to rethink our assumptions about reality and question the very nature of existence. It is a field that is constantly evolving, with new discoveries and insights emerging every day. The study of quantum mechanics is a journey into the unknown, a quest to uncover the deepest secrets of the universe. It is a journey that requires an open mind, a willingness to embrace uncertainty, and a passion for discovery. Quantum mechanics, often described as the physics of the very small, delves into the behavior of matter and energy at the atomic and subatomic levels. It is a field that explores the fundamental building blocks of the universe and seeks to understand the forces that govern their interactions. The study of quantum mechanics has led to some of the most profound discoveries in the history of science, and it continues to push the boundaries of our knowledge and understanding. Delves into the behavior of matter and energy at the atomic and subatomic levels. It is a realm where the classical laws of physics no longer apply and where the behavior of particles is governed by the principles of quantum mechanics. This field of study has revolutionized our understanding of the universe and has led to groundbreaking discoveries that have transformed technology and changed the way we live. From the development of quantum computers to the creation of new materials, the principles of quantum mechanics are shaping the future in ways that we are only beginning to comprehend. It's a realm where our everyday experiences no longer hold true, and where the behavior of particles defies our classical understanding of reality. In the quantum world, particles can exist in multiple states simultaneously, and their behavior is governed by probabilities rather than certainties. This challenges our classical notions of space and time and opens up a world of possibilities that are both fascinating and perplexing. The study of quantum mechanics is a journey into the unknown, a quest to uncover the deepest secrets of the universe. And particles like electrons and photons dance to a different tune, a quantum tune. In the quantum world, particles do not follow the predictable paths we are accustomed to. Instead, they exist in a state of uncertainty, governed by probabilities rather than certainties. This is the world of quantum mechanics, where the classical laws of physics give way to a new set of rules. It is a world that is both surreal and captivating, where the impossible becomes possible and the unimaginable becomes reality. This is your invitation to embark on a journey into the heart of quantum mechanics, a journey that will challenge your perceptions and ignite your imagination. The study of quantum mechanics is a quest to uncover the deepest secrets of the universe, to understand the fundamental principles that govern the behavior of matter and energy at the atomic and subatomic levels. It is a journey that requires an open mind, a willingness to embrace uncertainty, and a passion for discovery. A journey that will challenge your perceptions and ignite your imagination. The study of quantum mechanics is a quest to uncover the deepest secrets of the universe, to understand the fundamental principles that govern the behavior of matter and energy at the atomic and subatomic levels. It is a journey that requires an open mind, a willingness to embrace uncertainty, and a passion for discovery. Prepare to explore the fundamental principles that govern the universe's smallest constituents, unraveling the mysteries of superposition, entanglement, and the wave-particle duality. These concepts are at the heart of quantum mechanics, and they have profound implications for our understanding of reality. The study of quantum mechanics is a journey into the unknown, a quest to uncover the deepest secrets of the universe. It is a journey that requires an open mind, a willingness to embrace uncertainty, and a passion for discovery. Unraveling the mysteries of superposition, entanglement, and the wave-particle duality. These concepts are at the heart of quantum mechanics, and they have profound implications for our understanding of reality. The study of quantum mechanics is a journey into the unknown, a quest to uncover the deepest secrets of the universe. It is a journey that requires an open mind, a willingness to embrace uncertainty, and a passion for discovery. In our everyday world, we perceive objects as solid, stable, and predictable. We go about our daily lives interacting with these objects, often without giving them a second thought. The chair we sit on, the table we eat at, the phone we use, all these items seem to follow a set of rules that we have come to understand intuitively. We expect a chair to support our weight, a table to hold our belongings, and a phone to function as a communication device. These expectations are based on our experiences and the laws of classical physics that govern the macroscopic world. A ball thrown into the air follows a defined path, tracing a predictable arc as it succumbs to the forces of gravity and air resistance. This trajectory can be calculated with precision using Newton's laws of motion, which have been the cornerstone of classical mechanics for centuries. These laws allow us to predict the future position and velocity of the ball at any given moment, provided we know its initial conditions. This predictability gives us a sense of control and understanding over the physical world, and a dropped glass shatters into predictable fragments. The moment the glass slips from our hand, we can anticipate the outcome. It will fall to the ground, break into pieces, and scatter across the floor. This event, though seemingly chaotic, follows the deterministic principles of classical physics. The energy transfer, the impact, and the resulting fragmentation can all be explained through well-established physical laws. This predictability is comforting as it aligns with our everyday experiences and expectations. This classical view of reality, governed by Isaac Newton's laws of motion, served us well for centuries. Newton's laws provided a framework for understanding the macroscopic world, from the motion of planets to the mechanics of everyday objects. These laws were instrumental in the development of engineering, technology, and various scientific disciplines. They allowed us to build bridges, design machines, and explore the cosmos with confidence in our ability to predict and control physical phenomena. However, as physicists delved deeper into the microcosm, they encountered phenomena that defied classical explanations. The discovery of the atom and its constituent particles revealed a world that was far more complex and mysterious than previously imagined. At these minuscule scales, the deterministic laws of classical physics no longer held true. Instead, scientists observed behaviors that were probabilistic and often counterintuitive, challenging the very foundations of our understanding. At the atomic and subatomic levels, the familiar rules of classical physics break down. Particles such as electrons, protons, and neutrons do not behave like tiny billiard balls following predictable paths. Instead, they exhibit dual characteristics, sometimes acting like particles and other times like waves. This duality is a fundamental aspect of quantum mechanics, a branch of physics that seeks to explain the behavior of matter and energy at the smallest scales. Particles, the fundamental building blocks of matter, no longer behave like tiny billiard balls. In classical physics, particles are seen as discrete entities with well-defined positions and velocities. However, in the quantum realm, particles can exist in multiple states simultaneously, a phenomenon known as superposition. This means that a particle can be in different places or have different properties at the same time, a concept that defies our everyday experiences and intuitions. Instead, they exhibit wave-like properties, their behavior governed by probabilities rather than certainties. The wave-particle duality of quantum objects means that they can interfere with themselves, creating patterns that are characteristic of waves. This probabilistic nature is described by the wave function, a mathematical representation that encapsulates all possible states of a particle. The wave function does not provide a definite answer about the particle's position or momentum, but rather a probability distribution of where it might be found. This radical departure from classical physics marked the birth of quantum mechanics. Quantum mechanics introduced a new set of principles that govern the behavior of particles at the smallest scales. These principles include superposition, entanglement, and uncertainty, each of which challenges our classical notions of reality. Superposition allows particles to exist in multiple states simultaneously, while entanglement creates correlations between particles that are instantaneously connected, regardless of distance. The uncertainty principle, formulated by Werner Heisenberg, states that certain pairs of properties, such as position and momentum, cannot be simultaneously known with arbitrary precision. Imagine a world where a single particle, like an electron, can exist in multiple states simultaneously. This is not a mere limitation of our measurement tools, but a fundamental aspect of nature. In this quantum world, particles do not have definite properties until they are observed. The act of measurement collapses the wave function, forcing the particle to choose a specific state. This idea, known as the observer effect, implies that the very act of observation plays a crucial role in determining the outcome of quantum events. It's not that we don't know its exact state, it's that the electron itself exists in a superposition of states, a concept that challenges our very notion of reality. Superposition allows particles to be in a combination of all possible states until a measurement is made. This leads to phenomena such as quantum interference, where particles can interfere with themselves, creating patterns that are impossible to explain using classical physics. The famous double-slit experiment demonstrates this, showing that particles can behave like waves, creating interference patterns even when fired one at a time. Quantum mechanics forces us to abandon our classical intuitions and embrace a new set of rules that are often non-intuitive and perplexing. These rules have profound implications for our understanding of the universe. They suggest that reality is not deterministic but probabilistic, and that particles can be connected in ways that transcend classical notions of space and time. This new framework has led to a deeper understanding of the fundamental nature of reality, revealing a universe that is far more interconnected and dynamic than previously imagined, a set of rules that govern the universe at its most fundamental level. These quantum rules apply not only to subatomic particles but also to the very fabric of space and time. They have led to the development of quantum field theory, which describes how particles interact with fields that permeate the universe. This theory has been instrumental in the discovery of new particles and forces, providing a unified framework for understanding the fundamental interactions that govern the cosmos. These rules, often counterintuitive and perplexing, have led to groundbreaking discoveries and technological advancements that are shaping our world in profound ways. Quantum mechanics has given rise to technologies such as quantum computing, which promises to revolutionize information processing by harnessing the power of superposition and entanglement. Quantum cryptography offers unprecedented security for communication, while quantum sensors provide unparalleled precision in measurement. These advancements are just the beginning, as the principles of quantum mechanics continue to inspire new innovations and deepen our understanding of the universe. To grasp the essence of quantum mechanics, we must venture beyond the familiar macroscopic world and peer into the realm of atoms and the particles within them. This is a realm where energy exists in discrete packets called quanta, where particles exhibit wave-particle duality and where uncertainty reigns supreme. Imagine an electron orbiting an atom's nucleus, not as a miniature planet around a star, but as a blurry cloud of probability. This cloud represents the electron's wave function, a mathematical description encompassing all its possible states. Unlike classical physics, which predicts an object's precise location and momentum, quantum mechanics deals in probabilities, suggesting that the electron is smeared out across space until measured. This inherent uncertainty, enshrined in Heisenberg's uncertainty principle, is a fundamental aspect of quantum mechanics. It states that we can never simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one, the less we know about the other. The quantum realm challenges our perception of reality, suggesting that the act of observation itself influences the observed system. It's a world of probabilities where the very act of measurement collapses the wave function, forcing the particle into a definite state. Quantum mechanics is not merely an esoteric branch of physics, it's the foundation upon which our understanding of the universe rests. This field, which delves into the behavior of particles at the smallest scales, has revolutionized our comprehension of reality. It challenges our classical intuitions and reveals a world that is both perplexing and profoundly beautiful. The principles of quantum mechanics are not confined to the microscopic realm. They have far-reaching implications that touch every aspect of our existence, from the behavior of subatomic particles to the fusion reactions that power the stars. Quantum mechanics provides the framework for explaining the universe's workings at their most fundamental level. These reactions, occurring in the hearts of stars, are a testament to the power of quantum principles. The fusion process, where lighter elements combine to form heavier ones, releases vast amounts of energy, illuminating the cosmos and driving the life cycles of stars. Without quantum mechanics, our understanding of these stellar processes would be incomplete. Consider the Sun, a giant ball of plasma where hydrogen atoms fuse to form helium, releasing an immense amount of energy in the process. This energy radiating outward is what makes life on Earth possible. The Sun's surface, with its dynamic solar flares and turbulent plasma, is a direct consequence of the quantum interactions occurring deep within its core. These interactions are governed by the probabilistic nature of quantum mechanics, where particles exist in a state of superposition, only collapsing into a definite state upon measurement. This nuclear fusion, the very process that sustains life on Earth, is governed by quantum mechanics. In laboratories around the world, scientists are striving to replicate this process to create a sustainable and nearly limitless source of energy. Fusion reactors, with their glowing reactions, are a testament to human ingenuity and our quest to harness the power of the stars. The challenges are immense, but the potential rewards are even greater, promising a future where energy is abundant and clean. The interactions between protons and neutrons within the Sun's core, overcoming their electrostatic repulsion to fuse and release energy, are dictated by the laws of the quantum world. These particles, bound by the strong nuclear force, must overcome significant barriers to come together. Quantum tunneling, a phenomenon where particles pass through energy barriers they seemingly shouldn't be able to, plays a crucial role in this process. It's a vivid demonstration of how quantum mechanics defies our classical expectations. Quantum mechanics is also crucial for understanding the behavior of materials. The conductivity of metals, which allows for the flow of electric current, is a direct result of the quantum behavior of electrons. In a metal lattice, electrons move freely, creating a sea of charge that can be harnessed for various applications. This understanding has paved the way for countless technological advancements, from simple electrical circuits to complex computing systems. The properties of semiconductors that power our electronic devices, from smartphones to supercomputers, are also governed by quantum mechanics. Semiconductors, with their unique ability to conduct electricity under certain conditions, are the backbone of modern electronics. The precise control of electron flow in these materials is achieved through an intricate understanding of quantum principles, enabling the miniaturization and enhancement of electronic components. And the very existence of chemical bonds are all consequences of quantum mechanics. The way atoms come together to form molecules, creating the vast array of substances we encounter daily, is dictated by the interactions of their electrons. These bonds, whether covalent, ionic, or metallic, are the result of quantum forces at play. Understanding these interactions has allowed chemists to manipulate matter at the molecular level, leading to innovations in medicine, materials, science, and beyond. The way electrons arrange themselves within atoms, forming bonds and determining a material's properties, is dictated by the quantum rules that govern their behavior. Electrons occupy discrete energy levels, and their arrangements determine the chemical and physical properties of elements. This quantum behavior is the foundation of the periodic table, guiding the interactions that lead to the diversity of matter in the universe. By studying these arrangements, scientists can predict and create new materials with tailored properties. By unraveling the mysteries of the quantum realm, we gain a deeper appreciation for the universe's elegance and complexity. The abstract representations of quantum particles, often depicted as waves or clouds of probability, challenge our perceptions and invite us to explore the unknown. These visualizations, though complex, offer a glimpse into the underlying order of the cosmos, where seemingly random events are governed by precise mathematical laws. Quantum mechanics provides the key to understanding the very fabric of reality, from the smallest subatomic particles to the grandest cosmic structures. It bridges the gap between the micro and macro, revealing a universe that is interconnected and interdependent. As we continue to explore and expand our knowledge, the principles of quantum mechanics will undoubtedly lead to new discoveries, transforming our understanding of the world and our place within it. The journey of unraveling the universe's secrets is ongoing, and each revelation brings us closer to comprehending the true nature of reality. Section 5. A paradigm shift, challenging classical physics. The early 20th century was a time of great upheaval and transformation in the world of physics. The established principles of classical physics, which had reigned supreme for centuries, were suddenly called into question by a series of groundbreaking discoveries and theories. This period marked the beginning of a new era in scientific thought, one that would forever change our understanding of the universe and the fundamental nature of reality. The development of quantum mechanics in the early 20th century marked a profound paradigm shift in scientific thought. This new framework emerged from the collective efforts of brilliant minds such as Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, among others. These pioneers of quantum theory sought to explain phenomena that classical physics could not, leading to a radical rethinking of the laws that govern the natural world. Classical physics, with its deterministic laws and predictable outcomes, proved inadequate for describing the strange and counterintuitive behavior of the quantum world. The classical view, rooted in the works of Isaac Newton and James Clerk Maxwell, depicted a universe where objects followed precise trajectories and events unfolded in a predictable manner. However, this deterministic framework began to crumble as scientists delved deeper into the subatomic realm. Imagine the scientific community's astonishment when experiments revealed that light, long considered a wave, could also behave like a particle. This duality was first hinted at by Einstein's explanation of the photoelectric effect, where light striking a metal surface emitted electrons, suggesting that light could be thought of as discrete packets of energy or photons. This wave-particle duality was further confirmed by the famous double-slit experiment, which demonstrated that light could produce interference patterns characteristic of waves, yet also exhibit particle-like behavior when observed. This wave-particle duality, a central tenet of quantum mechanics, shattered the classical dichotomy between waves and particles, forcing physicists to rethink their fundamental understanding of nature. The realization that entities, such as electrons and photons, could exhibit both wave-like and particle-like properties depending on the experimental context was a profound departure from classical intuition. It introduced a level of uncertainty and indeterminacy that was previously unimaginable. Similarly, the discovery of quantum entanglement, where two particles become linked in such a way that they share the same fate regardless of the distance separating them, challenged the very notion of locality. This phenomenon, first described by Einstein, Podolsky and Rosen in their famous EPR paper, suggested that particles could instantaneously affect each other's states, even when separated by vast distances. This spooky action at a distance, as Einstein called it, seemed to defy the principle of local realism, which states that an object can only be influenced by its immediate surroundings. Einstein famously referred to entanglement as spooky action at a distance, as it seemed to violate the principle of local realism, which states that an object can only be influenced by its immediate surroundings. Despite Einstein's discomfort with the implications of quantum mechanics, subsequent experiments, such as those conducted by Alain Aspect in the 1980s, provided strong evidence for the reality of entanglement, further solidifying its place as a cornerstone of quantum theory. quantum mechanics forced physicists to abandon their classical intuitions and embrace a new set of rules. Rules that often defied common sense, but were nonetheless consistent with experimental observations. The Heisenberg uncertainty principle, for example, stated that one could never simultaneously know both the exact position and momentum of a particle. This inherent uncertainty was not due to experimental limitations, but was a fundamental aspect of nature itself. Similarly, Schrödinger's wave equation provided a probabilistic description of a particle's behavior, emphasizing the role of probability and uncertainty in the quantum realm. This paradigm shift revolutionized our understanding of the universe, opening up new avenues of exploration and leading to groundbreaking technological advancements. Quantum mechanics has given rise to technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI, which have become integral to modern life. Moreover, the ongoing research in quantum computing and quantum cryptography promises to usher in a new era of technological innovation, with the potential to solve complex problems and enhance security in ways that were once thought impossible. The journey from classical to quantum physics has not only deepened our understanding of the natural world, but has also paved the way for a future where the possibilities are limited only by our imagination. Section 6, the quantum dance where particles defy logic. In this section, we delve into the mysterious and often perplexing world of quantum mechanics, a realm where the rules of classical physics seem to be turned on their head. Here, particles behave in ways that defy our everyday understanding of reality, engaging in a mesmerizing dance that challenges our very notions of existence and observation. In the quantum realm, particles engage in a captivating dance, defying our classical expectations and exhibiting behaviors that seem nothing short of magical. This dance is not just a metaphor, but a literal description of how particles move and interact on the smallest scales. Unlike the predictable paths of planets orbiting a star, quantum particles follow probabilistic patterns, appearing to be in multiple places at once and changing their state in response to observation. Particles exist in a superposition of states occupying multiple positions and possessing multiple properties simultaneously, until the act of measurement collapses their wave function into a single definite state. This phenomenon, known as superposition, is one of the cornerstones of quantum mechanics. It suggests that particles do not have a definite position or state until they are observed, existing instead in a cloud of probabilities. This idea is so counterintuitive that it has puzzled and fascinated scientists for decades. Imagine a single photon, a particle of light passing through two slits simultaneously. This is not a mere thought experiment, but a real phenomenon observed in countless laboratories worldwide. The double-slit experiment, first conducted by Thomas Young in the early 19th century, has become one of the most famous and perplexing experiments in the history of science. It reveals the dual nature of light, behaving both as a particle and a wave. This is not a thought experiment, but a real phenomenon observed in countless laboratories worldwide. When a single photon is fired at a barrier with two slits, it appears to pass through both slits at the same time, creating an interference pattern on a screen behind the barrier. This pattern is characteristic of waves, not particles, suggesting that the photon is somehow interfering with itself. This wave-particle duality is one of the most intriguing aspects of quantum mechanics. The double-slit experiment, a cornerstone of quantum mechanics, demonstrates the wave-particle duality of light, showing that a single photon can interfere with itself, creating an interference pattern on a screen behind the slits. This experiment has profound implications for our understanding of reality. It suggests that particles do not have a single, well-defined path, but instead explore all possible paths simultaneously. This idea is so strange that even Albert Einstein, one of the founders of quantum mechanics, found it difficult to accept. This interference pattern, a hallmark of wave behavior, arises because the photon doesn't choose a single path, but rather explores all possible paths simultaneously, interfering with itself along the way. This concept, known as wave-particle duality, is one of the most fundamental principles of quantum mechanics. It suggests that particles can exhibit both wave-like and particle-like properties, depending on how they are observed. This duality is not limited to photons, but applies to all quantum particles. It's as if the photon travels through both slits simultaneously, even though it's a single, indivisible particle. This paradoxical behavior is a direct consequence of the principles of quantum mechanics. It challenges our classical intuition and forces us to rethink our understanding of reality. In the quantum world, particles do not follow the deterministic paths of classical physics, but instead exist in a state of probability, only taking on definite properties when observed. This counterintuitive behavior is not limited to light. Electrons, protons, and even entire atoms have been shown to exhibit wave-like properties, interfering with themselves and creating interference patterns in experiments. This wave-particle duality is a universal feature of the quantum world, applying to all particles regardless of their size or mass. It suggests that the behavior of particles is governed by the principles of quantum mechanics, which are fundamentally different from the laws of classical physics. Electrons, protons, and even entire atoms have been shown to exhibit wave-like properties, interfering with themselves and creating interference patterns in experiments. This phenomenon has been observed in a wide range of experiments, from the double-slit experiment to more complex setups involving multiple particles. It suggests that the quantum world is governed by a different set of rules where particles can exist in multiple states and follow multiple paths simultaneously. The quantum world is a realm where particles dance to a different tune, a tune governed by probabilities and wave functions rather than classical trajectories. In this world, particles do not have definite positions or velocities, but instead exist in a cloud of probabilities, only taking on definite properties when observed. This probabilistic nature of quantum mechanics is one of its most intriguing and perplexing features, challenging our classical notions of reality and forcing us to rethink our understanding of the universe. Another fascinating aspect of the quantum world is entanglement, a phenomenon where particles become interconnected in such a way that the state of one particle is instantly correlated with the state of another, no matter how far apart they are. This spooky action at a distance, as Einstein called it, suggests that particles can communicate instantaneously, defying the classical notion that information cannot travel faster than the speed of light. Entanglement has been experimentally verified and is a key feature of quantum mechanics, with potential applications in quantum computing and cryptography. Quantum computing is one of the most exciting applications of quantum mechanics. Unlike classical computers, which use bits to represent information as either 0 or 1, quantum computers use qubits, which can exist in a superposition of states representing both 0 and 1 simultaneously. This allows quantum computers to perform complex calculations much faster than classical computers, potentially revolutionizing fields such as cryptography, materials science, and artificial intelligence. Quantum cryptography is another promising application of quantum mechanics. It uses the principles of quantum entanglement and superposition to create secure communication channels that are theoretically immune to eavesdropping. Quantum key distribution, for example, allows two parties to share a secret key with complete security, as any attempt to intercept the key would disturb the quantum states and be immediately detected. Quantum teleportation is a process by which the state of a particle can be transmitted from one location to another without physically moving the particle itself. This is achieved through quantum entanglement, where the state of one particle is instantaneously transferred to another, regardless of the distance between them. While quantum teleportation does not involve the physical transport of matter, it has potential applications in quantum communication and computing, allowing for the transfer of quantum information with high fidelity. The quantum world is a realm of endless possibilities, where particles defy our classical expectations and exhibit behaviors that seem almost magical. From superposition and entanglement to wave-particle duality and quantum teleportation, the principles of quantum mechanics challenge our understanding of reality and open up new frontiers in science and technology. As we continue to explore this mysterious realm, we are likely to uncover even more surprising and profound insights into the nature of the universe. The dance of particles in the quantum realm is a testament to the beauty and complexity of the universe. It reminds us that our understanding of reality is constantly evolving and that there is always more to discover. As we continue to probe the depths of the quantum world, we are not only expanding our knowledge of the universe, but also pushing the boundaries of what is possible. paving the way for new technologies and insights that could transform our world. In conclusion, the quantum dance is a fascinating and mysterious phenomenon that challenges our classical understanding of reality. It reveals a world where particles can exist in multiple states, follow multiple paths, and communicate instantaneously across vast distances. This quantum realm is governed by probabilities and wave functions, offering a glimpse into the underlying fabric of the universe. As we continue to explore this enigmatic world, we are likely to uncover even more profound and surprising insights into the nature of reality. Section 7. Embracing the unknown, a journey into uncertainty. Uncertainty is not a flaw in quantum mechanics, but rather a fundamental aspect of the theory. Unlike classical physics, which aims to predict events with absolute certainty, quantum mechanics embraces uncertainty, acknowledging that we can never know both the position and momentum of a particle with perfect accuracy. Heisenberg's uncertainty principle, a cornerstone of quantum mechanics, places fundamental limits on our ability to measure the properties of particles. It's not a limitation of our instruments, but rather a fundamental property of nature. The act of measurement itself disturbs the system being measured, introducing an inherent uncertainty into our observations. Imagine trying to pinpoint the location of an electron orbiting an atom. The very act of observing the electron, perhaps by shining light on it, would impart momentum to the electron, altering its trajectory and introducing uncertainty into our measurement of its position. The more precisely we try to measure its position, the more we disturb its momentum, and vice versa. This inherent uncertainty does not render quantum mechanics useless, but rather highlights its probabilistic nature. Quantum mechanics provides us with probabilities, not certainties. It tells us the likelihood of finding a particle in a particular state, not its precise location or momentum. Section 8. From Enigma to Innovation, Quantum Mechanics in Action. Quantum mechanics, once considered an esoteric branch of physics confined to the realm of theoretical speculation, has emerged as a driving force behind some of the most groundbreaking technological advancements of our time. The journey of quantum mechanics from a theoretical framework to practical applications is a fascinating tale of human ingenuity and scientific curiosity. It all began in the early 20th century when physicists like Max Planck and Albert Einstein started to unravel the mysteries of the subatomic world. Their pioneering work laid the foundation for a new understanding of nature, one that defied the classical laws of physics and introduced concepts that were both perplexing and revolutionary. From lasers and transistors to medical imaging and quantum computing, quantum mechanics is transforming our world in profound ways. The principles of quantum mechanics have been harnessed to develop technologies that were once the stuff of science fiction. Lasers, for instance, have become ubiquitous in our daily lives, finding applications in everything from barcode scanners and DVD players to advanced surgical procedures and telecommunications. The development of the transistor, another marvel of quantum mechanics, has revolutionized the field of electronics, leading to the creation of microchips that power our computers, smartphones, and countless other devices. Consider the laser, a device that emits a highly focused beam of coherent light. The invention of the laser in the 1960s was a direct result of understanding the quantum mechanical phenomenon of stimulated emission. This process, where an excited atom can be stimulated to emit a photon by interacting with an identical photon, is a cornerstone of quantum mechanics. The coherent light produced by lasers has unique properties that make it invaluable for a wide range of applications. In telecommunications, lasers are used to transmit data over long distances with minimal loss, enabling the high-speed internet connections we rely on today. Lasers rely on the quantum mechanical phenomenon of stimulated emission, where an excited atom can be stimulated to emit a photon by interacting with an identical photon. This process, impossible to explain using classical physics, is the foundation of laser technology, enabling applications ranging from telecommunications and barcode scanners to laser surgery and optical storage devices. In the medical field, lasers are used for precision surgeries, allowing doctors to perform procedures with minimal invasiveness and faster recovery times for patients. Optical storage devices such as CDs and DVDs use lasers to read and write data, revolutionizing the way we store and access information. This process, impossible to explain using classical physics, is the foundation of laser technology, enabling applications ranging from telecommunications and barcode scanners to laser surgery and optical storage devices. The versatility of lasers is a testament to the power of quantum mechanics. In addition to their practical applications, lasers have also become essential tools in scientific research, allowing scientists to probe the fundamental properties of matter and explore new frontiers in physics and chemistry. The ability to manipulate light at the quantum level has opened up new possibilities for innovation and discovery. Another example is the transistor, the building block of modern electronics. The invention of the transistor in the mid-20th century marked a turning point in the history of technology. Transistors, which amplify or switch electronic signals, rely on the quantum mechanical behavior of electrons in semiconductors. This breakthrough paved the way for the development of integrated circuits, which are the heart of modern electronic devices. The miniaturization of transistors has enabled the creation of powerful and compact devices that have transformed the way we live, work, and communicate. Transistors, which amplify or switch electronic signals, rely on the quantum mechanical behavior of electrons in semiconductors. The flow of electrons through a transistor is controlled by manipulating their quantum states, a feat impossible to achieve using classical concepts alone. This ability to control electron flow with precision has led to the development of microprocessors, which are the brains of computers and other digital devices. Microprocessors have revolutionized industries ranging from computing and telecommunications to automotive and aerospace, driving innovation and economic growth. The flow of electrons through a transistor is controlled by manipulating their quantum states, a feat impossible to achieve using classical concepts alone. This quantum control has enabled the creation of increasingly powerful and efficient electronic devices. The rapid advancement of semiconductor technology has led to the development of smaller, faster, and more energy-efficient transistors, which are essential for the continued progress of the digital age. As we push the boundaries of miniaturization, quantum mechanics will continue to play a crucial role in shaping the future of electronics. Quantum mechanics is also revolutionizing the field of medicine. One of the most significant contributions of quantum mechanics to medical science is the development of magnetic resonance imaging, or MRI. This widely used medical imaging technique exploits the quantum mechanical properties of atomic nuclei to produce detailed images of the body's internal structures. MRI has become an indispensable tool in the diagnosis and treatment of a wide range of medical conditions, providing doctors with critical information that was previously inaccessible. Magnetic resonance imaging, or MRI, a widely used medical imaging technique, exploits the quantum mechanical properties of atomic nuclei to produce detailed images of the body's internal structures. MRI relies on the fact that the nuclei of certain atoms, when placed in a strong magnetic field, absorb and re-emit radio waves at specific frequencies, providing valuable diagnostic information. This non-invasive imaging technique allows doctors to visualize soft tissues such as the brain, muscles, and organs with remarkable clarity, aiding in the early detection and treatment of diseases. MRI relies on the fact that the nuclei of certain atoms, when placed in a strong magnetic field, absorb and re-emit radio waves at specific frequencies, providing valuable diagnostic information. The ability to image the body's internal structures with such precision has revolutionized medical diagnostics and treatment. MRI has become a standard tool in hospitals and clinics around the world, helping doctors to diagnose conditions ranging from brain tumors and spinal cord injuries to joint disorders and cardiovascular diseases. The ongoing advancements in MRI technology continue to improve its accuracy and expand its applications in medical science. These examples highlight the profound impact of quantum mechanics on our technological landscape. The principles of quantum mechanics have not only led to the development of groundbreaking technologies, but have also deepened our understanding of the universe. Quantum mechanics has challenged our classical notions of reality, introducing concepts such as wave-particle duality, superposition, and entanglement. These ideas have not only revolutionized physics, but have also inspired new ways of thinking in fields such as chemistry, biology, and computer science. From the devices we use daily to the frontiers of scientific research, quantum mechanics is shaping our world in ways that were once unimaginable. The ongoing research in quantum mechanics holds the promise of even more transformative technologies in the future. Quantum computing, for example, has the potential to solve complex problems that are currently beyond the reach of classical computers. Quantum communication and cryptography could revolutionize the way we secure and transmit information. As we continue to explore the mysteries of the quantum world, we can expect to see new innovations that will further enhance our lives and expand our understanding of the universe.